Welcome back. Last video for chapter 9. I wish I could say there was some high-tech reason that I didn't finish the whole chapter in one video, but really it was just my wife came out and saw that I was recording a video and thought it'd be funny to mess with me while I was trying to finish a recording. So unfortunately, we're going to finish this in 2 videos. So here's the second one. We left off talking about bond enthalpy, or the energy that you would need to input to break a bond. And we showed that how our delta H was increasing with double bonds and triple bonds. Now it took a lot more energy to break a triple bond than it did to take a double bond. And so that's where we left off. Average bond enthalpy in polyatomic molecules is really not too bad. You look at water, gas, and you say, okay, if we were to break that into individual atoms, our first step would be to break hydrogen and an OH group. Our second step would be to take that OH group and break it into hydrogen and oxygen. And if we can get the delta H for each individual step, then you just find the average. It really is just as easy as that. Add the 2 and divide by 2. That's average bond enthalpy. 464 kilojoules. It's not too terrible. Here's a chart you can find in your book that shows you bond enthalpies of some pretty common chemicals. So changes in reactions. One way to think about enthalpy change, we've already done in thermodynamics the whole like delta H of all products minus delta H of all reactants. That's the old way of doing it. It's a little more complicated, but it still works. Imagine a reaction proceeds by first you break every bond in all your reactants, then you use all those gaseous reactant atoms to form all the bonds in your products. And so you can say our delta H is how much energy we put into this reaction minus the energy we released from the reaction. And so then they put that here as the sum of the bond enthalpies of all your reactants minus the sum of the bond enthalpies of all of your products. Now note that this is reactants minus products because the last time we saw delta H, it was products minus reactants. So try not to get too mixed around with that. And so here you have a chart for an endothermic reaction where you have the bond enthalpies of all your reactants going to atoms, atoms reforming, bond enthalpies of all your products, where all your products are. And so the enthalpy has increased from reactants to products. Here, reactants and our bond enthalpies of all of our reactants to gaseous atoms, all the gaseous atoms forming products, and the net change from our reactants to products has been to release some heat, a negative enthalpy, and so that's exothermic. There's an example of how you might do this. We say, okay, we have hydrogen gas, we have chlorine gas, and we break them apart into individual gas atoms. And then here's the same idea with hydrogen gas and oxygen gas. We break them apart, and then we recombine a single oxygen, or a single hydrogen rather with an oxygen, another single hydrogen with an oxygen to make water. So that's kind of how we're visualizing this. Break the bond, reform the bonds to make our products. And that's how we're thinking about that. So here's how you would do this. Hydrogen gas, fluorine gas makes hydrofluoric acid as a gas. So we get all the bond enthalpies for our reactants, these guys over here. We get all the bond enthalpies for all our products, this one guy over here. And so to do this, we took a hydrogen bond. We broke one hydrogen bond in our reactants. And the bond enthalpy was 436.4. We also had to break a fluorine bond, and that was 156.9. And then we look at what are we forming? Well, we're forming a bond between hydrogen and fluorine. So there's that bond, but we're forming 2 of them. There's our coefficient 2. And so our bond enthalpy there would be 568, and we multiply it by 2, and we get 1136.4. So then we just take our reactants minus our product, and we get a net change of negative 543.1 kilojoules per mole. And you'd have to look those up in an enthalpy chart in the back of your book.